So hey guys, I'm Kate Cavanaugh. I'm sorry about the confusion with the names. I'm a graduate student in, oh, can you see my screen okay?
Yes, we can see you.
Okay, cool. I'm a graduate student in Kyle Cavanaugh's lab at UCLA. We have the same last name and the same initials, so it can get a little bit confusing. We're not related, but we both work in kelp canopy systems. And today I'm going to be talking a little bit about some of the multi-scale approaches that our lab uses to understand kelp canopy dynamics in California. So for those of you who aren't familiar with kelp forests, they're important foundation species that shape the community dynamics and habitat of their local environment. And this is a really iconic image of a kelp forest that's a good example of their habitat structure. So kelp individuals have holdfasts that anchor them to the substrate. And then from these holdfasts grow fronds and blades. And you can think about fronds kind of like stems on a plant and blades like leaves. Each of these blades is buoyed to the surface with a pneumaticist, or this tiny little gas bladder. So they're actually able to extend through the water column and create this 3D structured habitat. And as they grow through the water column, the blades eventually reach the water surface, which make these systems amenable for using remote sensing to study their attributes and dynamics and potentially drivers in some of these dynamics. This is a video off the coast of Santa Barbara of a large kelp forest, and using a drone image, you can see that these large floating canopies are easily observable using aerial data. And they're gorgeous. Our lab has done a lot of work in coordination with Tom Bell at Woods Hole, developing automated methods for detecting kelp canopy using satellite data such as Landsat. So the automation of this has enabled us to create these really large-scale data sets that span from Baja California all the way up to Washington and Oregon. And you can actually download these data for free from kelpwatch.org. You can specify an area of interest and explore quarterly kelp canopy dynamics from the 80s to present. And while these data have really helped our understanding of regional kelp canopy fluctuations, the 30 by 30 meter pixel size of Landsat does inhibit our analysis for specific applications. So for example, there was a really large marine heat wave that hit the west coast of North America from 2014 to 2016. And this heat wave was concurrent with changes to local water conditions. There was, of course, large seawater anomalies in temperature, and there was also decreased nutrients. And as a result, kelp canopy declined pretty rapidly and pretty extensively along the coastline. And in addition, purple urchins, which are a major grazer of kelp populations, increased. So there were really widespread kelp declines in California, and in some areas by as much as 95%. So in 2016, if you look at this figure that I have up on the screen, you can see that the remnant populations that were able to persist were really small and sparse. So we weren't actually able to use Landsat to study these kelp populations after the decline. And it's applications like these that have led our lab to start developing methods and really advance the science of using UAVs for studying kelp canopy systems. And sorry, this is just a figure showing that, Landsat really isn't able to detect these small sparse populations that are close to the coastline, and you really need higher resolution data. We have a number of systems that we use in our lab. We have the Phantom 3 and the Phantom 4. For those of you who are familiar, I know the Phantom 3 probably seems ancient at this point, but it does still collect really good RGB imagery with just a color camera. And we have the Matrice 1, 2, and 300 equipped with multispectral sensors like the Red Edge and the Altum. And then we also have a Matrice 600 that's equipped with a hyperspectral camera. It's the Headwall NanoSpec. And each of these different camera products are able to give us different estimations about the kelp canopy in general. So for example, we can use color data and multispectral data to get kelp canopy area. Multispectral data can be used to derive biomass. And then these hyperspectral sensors can give us much more detailed information about the canopy, including pigment concentrations, nitrogen content, and also sugar content. And I'm going to describe just a couple of applications that we've developed so far using some of these products, in addition to some of the methods that we've developed to create them. Like terrestrial applications, we use the traditional lawnmower pattern to collect imagery, but when you're imaging over water, it's really important to get high overlap. So I have 75 to 80% overlap on the screen here, but we really do use a baseline of about 85% overlap between our images. And probably the main difference between our coastal aquatic applications and your land applications is that sun glint does really bias our imagery. So if we're taking images of the water and the sun is almost directly overhead, the water will directly reflect the sunlight back into the sensor, and that sun glint will skew or almost completely obscure a lot of the pixels in our imagery. So we've developed methods for masking out this sun glint. So in each individual unstitched image, we automate the detection of sun glint, we create these masks, and we feed these masks into drone processing software that creates orthomosaics. And we can tell the software to ignore any tie points that are located within our masks. That way, it will only look for tie points that are found with unobscured imagery from sun glint. So on the right side of the screen, the figure I'm showing here is an example of an orthomosaic we created without our sun glint method, and then that same exact set of imagery with our sun glint method. And you can see that the detection of kelp canopy in image B is so much easier than the detection in image A, where you have these image artifacts from glint that would really hinder our detection. So once we have our unobscured imagery, I'm just showing an example here with an RGB image, but the same exact methodology will hold true for multispectral data as well. We apply simple vegetation indices such as NDVI or blue NDVI, or if it's RGB imagery, just even a simple subtraction between the red and the blue band would do the job. If you plot the histogram of your vegetation index, the histogram will actually show two main peaks, one containing the majority of the kelp pixels and one containing the majority of the water pixels. So we can automate the detection of where those two peaks occur and then find the midpoint to be used as a threshold for our classified image, just differentiating kelp from water. And this methodology has allowed us to apply drone imagery for a number of applications. For example, we've been able to characterize the Northern California collapse that I described earlier. We've participated in annual surveys since 2019 in collaboration with folks at the Nature Conservancy, as well as the Greater Farallones Marine Sanctuary. And these are the largest marine resource-focused surveys that are completed in California to date. We cover a large range of area in Northern California in Mendocino and Sonoma counties. And these repeat time series have allowed us to track the declines and the recoveries that Landsat was not able to capture. We also have ongoing monthly surveys at the Santa Barbara LTER. We've been doing these since 2018. And using these data, we've been actually able to capture really fine scale details in local senescence and recolonization patterns on this reef. Similarly, we've done biweekly surveys at Palos Verdes between June of 2018 and September of 2019. And these surveys allowed us to capture the local drivers of kelp beds in Southern California. So we correlated these with sea surface temperature and wave height, and both are strongly correlated with our drone surveys. So as sea surface temperature increases and the nutrient content in the water decreases, you can see a really sharp decline in kelp canopy. And as the water becomes to get a bit colder and kelp canopy increases, that canopy can actually get wiped out by large wave events. We also have used multispectral imagery for examining changes in canopy density, as well as local patterns of the environment. So the Altum sensor from MicaSense has 5 multispectral bands, as well as a thermal band. So from this sensor, not only are we able to get canopy density, but also we're able to look at the local seawater conditions that might be influencing the density of the canopy through time. And then the last set of imagery that I'm going to be talking about is hyperspectral imagery. And I saw on your schedule that Tom Bell is going to be talking tomorrow, so I'm sure that he'll go into a lot of detail about this as well. He also works in kelp canopy systems, but multispectral data gives you imagery in multiple bands with really wide bandwidths, whereas hyperspectral data gives you a really fine scale look at the reflectance of a scene across hundreds of wavelengths. And recent work that has come out using field data has shown that as kelp canopy ages, so I guess I should mention that kelp blades have a natural senescence period. So after 3 to 4 months, a blade will naturally die and then become replaced by new blades from the same plant. And as that blade begins to die, it starts to lose chlorophyll content, and that actually changes the spectral signature of the blade. So you can see that in this graph that I'm showing here. This mature blade is nice and dark and healthy and has a ton of photosynthetic pigments, whereas the senescence blade is much lighter in color. It's lost its photosynthetic pigments, and it's probably about to come off of the plant. And we can detect these changes using hyperspectral data. So our setup is a headwall nanospec. It covers data in the visible and near infrared between 400 and 1,000 nanometers. It has 270 spectral bands at a resolution of 2 to 3 nanometers, and it weighs about 1.5 pounds. So we can't fly it on one of the typical like Matrice 100, 200, or 300 that are used in a lot of labs. We use a Matrice 600, which is much bigger and a bit more complicated to fly, but it does have the capacity to carry this payload. There is pretty intense or labor-intensive setup for using this sensor. You have to do spectral field calibrations, and you also have to do post-processing field calibrations in order to get accurate reflectance measurements. So we've started collecting time series of hyperspectral imagery at a kelp bed off the coast of Santa Barbara, and we're interested in examining the physiological state of the canopy to map these local patterns of senescence and decline. So not only are we getting presence and absence, but we're actually getting ideas about the health of the canopy itself. Every time we've flown in conjunction with divers. So divers have gone out and collected canopy data for us, and then we can actually take lab measurements of blades and correlate them to our reflectance from the drone in order to make empirical relationships between the blade health and the reflectance that we're seeing with the nano hyperspec. The data are challenging to work with, to say the least. They image, or the sensor images in this sweeping pattern. So instead of the traditional lawnmower pattern that you've probably talked about in DroneCamp so far, and then running those individual scenes through some sort of orthomosaicing software, each of these scenes comes out in a line and has to be ortho-rectified and then spectrally corrected individually before being mosaiced together. And it's going to be challenging for us to make these relationships between the physiological state of the canopy and these reflectance data, because you can see how challenging even the ambient lighting conditions can make the imagery itself. So for example, that image on April 26th is really impacted by sun glint, and that's something that we're going to have to figure out how to modify for moving forward. So just in conclusion, we've come up with reliable methods for producing canopy area and biomass products from RGB and multispectral data. And these have helped us identify local areas of extinction and recolonization, as well as some of the drivers of local dynamics. And we're now working on models for estimating and validating physiological condition and nitrogen content from a headwall nanospec data. So thank you guys. That's all I have for you now. I'm going to turn it over to Kyle Emery to talk about some of the more land-focused coastal work that we're doing. And I think he and I will take questions together at the end.
Okay, so my name is Kyle Emery. I'm a recent postdoc addition to Kyle Cavanaugh's lab at UCLA. And today I'm going to talk about some new approaches to drone-based research in California's intertidal ecosystems. Okay, so just a brief outline for my talk. I'm going to give you some background to frame this work in a more ecological manner. Then I'm going to describe the surveys that we're doing on sandy beaches So the survey methods, how we're classifying the images, and some newer work with the elevation models that we're developing. And then I'll finish with a brief overview of some rocky intertidal restoration work that we're doing with rockweed. So here in Southern California, broadly, we have a really diverse assemblage of these coastal ecosystem types. There are many different systems found at very local scales, including salt marshes, beaches, kelp forests, and the rocky intertidal. And our lab at UCLA conducts drone-based research in all of these. But of these different coastal ecosystem types, sandy beaches are the most common, and they're the most abundant coastline worldwide, actually making up around 31% of ice-free shorelines. And they're especially common in population centers, Southern California being no exception. But they're really unique ecosystems because they're dependent on both terrestrial and marine influences. And as an ecosystem, they're also really unique in that they have, in most cases, little to no primary production. So there are instances of surf zone and intertidal diatoms, as well as dune vegetation, but the majority of the beach has no active primary producers. However, this is a really highly subsidized ecosystem with inputs of RAC from the nearshore environment. So RAC is like a catch-all term, including macroalgae, seagrass, and any other forms of organic matter that are cast ashore. But that supply of RAC is really dependent on beach geomorphology. So width and slope and other factors are really important for how that RAC is received and processed on beaches. So there are a number of different subsidy regimes worldwide, but interestingly, marine macroalgae to land is the largest of these cross-ecosystem carbon flows. And basically what I mean is any cross-boundary flow of organic matter. Marine macroalgae to land is on the order of kilograms of organic matter per square meter per year. And of these marine macroalgae to land subsidies, giant kelp to the beach is one of the largest. So this subsidy, this particular subsidy regime is the focus of my research, and it's a familiar sight on many Southern California beaches. So this subsidy is very dynamic across both space and time, and we still have very little understanding of that fine scale variation with respect to space and time. However, we've really identified that drone-based research can aid us here by enhancing our ability to survey not only more areas, but to survey those areas more frequently. And the reason we want to do this is to really better understand the input and retention of these kelp RAC subsidies to beaches because of its importance to the food web. So this figure is showing some work that we've done on the ground, which has identified that the amount of kelp that a beach receives is a really strong driver of the abundance of various trophic groups. So at the base level, invertebrates respond to these kelp subsidies, and that pattern is seen all the way up through shorebirds, and in other cases, small mammals and reptiles. So there are many organisms that live on the beach or travel to the beach to take advantage of this subsidy. So I've started some monitoring at our LTER sites, our long-term ecological research sites that correspond to kelp forest and beach data sets that have been ongoing for around 20 years now. And what we're aiming to do here is to basically validate drone-based measurements of kelp RAC to these on-the-ground transect-based measurements that have been ongoing. So the surveys that I'm going to describe today are all done with the Phantom 4 RTK. What's unique about these surveys, though, is that I'm flying at a very low altitude. So all these surveys are at 25 meters with an 80% image overlap. We're conducting these at low tide concurrently with our RAC and shorebird surveys. And our flights are flown as close to noon as possible. So unlike the flights over water that Kate described, we want the sun to be directly overhead to minimize any influence of shadows from rack or footprints or any other alteration on the beach surface. So with this data, we're generating orthomosaics and DEMs using Agisoft. And because of our low altitude and high image overlap, we're able to generate really high resolution products. So our orthomosaic pixel size is generally on the order of 7 millimeters, and our digital elevation model around 1.2 centimeters. So this is, let me see if I can, a quick flight overview of what our sites look like. So you can see the kelp on the beach as we fly overhead. So with each of these surveys, we're collecting on the order of 1,000 images that are then stitched together. And there's a particular area of interest within these surveys. So we're looking at the Sandy Beach above the water table line, or above the water table outcrop on the beach, and below the dune vegetation. So the area generally bounded by the black box on the screen. So with the clipped orthomosaics, we're then developing training data to classify this imagery. And we're actually able to do it with just some simple broad brush categories. So wet sand, dry sand, and then an all-encompassing rack. The training data and the orthomosaics are then run through a random forest classification in R. And then the output from that is brought back into ArcGIS, where we can calculate various statistics based on the area and cover of kelp rack. And we found with our initial survey so far that it's actually doing a really great job at identifying the kelp rack on the beach, everything from individual kelp blades or pieces of kelp blades up to these very large full kelp plants. So what I can do to give you a better example is just zoom in on a portion of this image, and you can see many different sizes of kelp rack within this scene. So there are whole plants in the top left corner, individual fronds where each little nematocyst or float is visible, and then even little pieces of kelp rack on the beach. And our classification process is doing a really great job at highlighting and identifying all of these into a kelp rack polygon data set that we can use to measure rack across the beach face. So during a typical beach survey, we're measuring kelp rack on 3 meter wide transects that run from the cliff to the ocean. But here with this image, with the products that we develop here, we have the ability to measure rack on many meter wide transects. So just in this example here, with 25 replicates of these, we can really get a much better constrained estimate of kelp cover on the beach, doing many more transects than what could be accomplished in a given field survey. And it lets us really hone in on that cover where we have relatively low error from transect to transect. So our goal will be to develop the relationship between the kelp surveys via drone and via on-the-ground beach surveys, and then compare those across the long-term data set that we have with the LTR. So in addition to the orthomosaics, we're also generating really high resolution digital elevation models. So you can see here, this is the same scene. We can again zoom in on that particular area of focus. And our goal here is to use these elevation models to generate estimates of kelp rack biomass, which we can again compare to the transect-based measurements, but will allow us to develop really beach scale estimates of kelp rack inputs. And this is something that will really aid in our estimates of kelp production, where that kelp goes when it's lost from the beach, and just getting a better overall idea of like the fate of kelp once it's no longer growing and attached out on the reef. So really our next steps here, we have our kelp area identified from the orthomosaics. We'll use the elevation data here where we can use the really high resolution elevation models to determine the height of the kelp rack above the beach surface. And then we'll use that height and area data to calculate the volume of each of these kelp rack polygons and convert that to biomass. So additionally, we know that various consumer groups respond to these kelp subsidies, in particular invertebrates, the beach hopper in the image on the lower left being a prime example. We know that they utilize the beach and the kelp rack both for habitat and food. And we know that we can identify kelp area from our drone surveys. But additionally, we're thinking about how can we use our drone surveys to quantify or identify these consumer populations and their response to the rack subsidies. So these are very active consumers in the intertidal, and they leave behind very visual signs of their consumption patterns. So when rack comes in almost on a nightly basis, it's very rapidly consumed by these organisms. And they're basically leaving a ghost-like silhouette around where the original kelp plant was prior to them consuming it. So what we can use with our imagery is basically the ability to identify where these organisms are consuming kelp and get a general idea of the intensity to which they're feeding on this kelp as it comes in. So you can see, using the same aerial imagery I was displaying before, it's very clear where in these images not only these organisms are going to the kelp and feeding, but as you can see in this image, I've indicated the bottom of their zone with the black arrows along the screen. They're mobile and they construct new burrows on a nightly basis. So the data that we can collect from this imagery will actually allow us to map and track the distribution of these organisms on the beach face with up to daily resolution, and really tracking how their behavior and distributions change at various scales, daily to tide series, seasonally, or annually. So to switch gears a little bit, I'm going to talk about a similar survey technique that we're using, but this time in the rocky intertidal, where we're using drone surveys to monitor the transplants and hopefully success of the transplants for a rockweed restoration project. So rockweed is a brown macroalgae that grows in the rocky intertidal, similar in some ways to giant kelp because it has a small holdfast that attaches it to the rocky reef, except this plant is fully exposed during low tide. So we're conducting similar surveys here, but we're, in addition to the two-dimensional flight plan, we're also flying a three-dimensional flight plan. So the difference here being the 2D flight flies in that one lawnmower pattern direction with the camera at a 90-degree angle. The 3D flight flies in one direction, and then again, perpendicular to that with that camera angled at 60 degrees. And the reason for the additional flight is to try and improve our elevation models because of the greater complexity of the rocky intertidal. So drone surveys were conducted earlier this year, before and immediately after the transplant of these rockweed plants to potential restoration sites. And we'll follow up with 1 and 2 year post-transplant surveys starting next year. So I just want to give you an overview of how these sites really differ in terms of their complexity. This site on this image that I just showed is very flat and has a gentle slope, so it's easy to resolve the ground surface here. This site, a little bit more in the distance in the image, has a lot of rocky overhangs, which cast shadows and make it a little bit more difficult to see the full area. And then this third site, while fully exposed, has really large boulders and outcrops that make it a very, very complex surface. For now, I'm just going to focus in on some very preliminary imagery that we've got from the first site. So here again is a clipped orthomosaic of the full site. So you can see, you know, just like on the beach, flying at this low altitude is providing us with these really clear high resolution images of the sites. And I can zoom in to our particular area of focus. And although not part of this project, it's really interesting. Here in the lower intertidal, you can even see purple urchins congregating along the waterline here in the lower intertidal. But the imagery is providing us a really great snapshot of our rockweed restoration plants. So every red box here is around one of these transplants. And additionally, we transplanted a separate band above and below this, more as an experimental effort to look at success in different tidal heights. But importantly, the surveys are providing us with great spatially referenced data on these plants that we can then use to track them across the broader landscape over the duration of this restoration project. And as I mentioned, we're also developing and using the digital elevation models with these surveys. So you can see within the elevation model, the plants that I described in the prior zone, but more importantly, we know where the transplants went spatially in these elevation models. And that'll aid us in our later steps down the road, where we'll use the digital elevation model and transplant survival across these landscapes to build a model of suitable habitat with respect to restoration of this intertidal species. So in summary, these high resolution orthomosaics and DEMs from low altitude drone flights are really going to enable really highly detailed mapping of these intertidal habitat features. And importantly, we're going to be calibrating all of these drone-based measurements to concurrent on-the-ground surveys that are happening at the same time the flights are being flown. And additionally, we're really looking forward to future surveys where we will attempt to elucidate these additional ecological features of the beach, such as the invertebrate distributions, densities, and feeding patterns that are provided to us with these really high resolution imagery and data sets that we're collecting. Okay, thank you. If you have any questions, Kate or I are both happy to answer any of these projects.
That was great. Are there any questions? Oh, Paul. What fraction? What's your estimate of the fraction of insect biomass in a given rack mass?
Yeah, it's hugely variable, but the way we track the invertebrate biomass is if you picture yourself walking down the beach, every step that you take, if that's a meter wide step that you're taking, that band from the cliff down to the water, that meter wide band can have over a kilogram of those organisms. So when you add it up to the beach scale, it's a huge amount of biomass. And they're processing kilograms of kelp per square meter per year on the beach.
This is a question for Kate. Are you using your kelp canopy polygons to just estimate surface biomass? Or are you also estimating the biomass of the entire stipe all the way down? And if you are, how are you doing that?
Yeah, so using diver data, there are relationships between canopy area and then actual forest biomass. So we're using those relationships to make additional relationships between spectra and biomass of the entire forest.
You had a question.
Hi, should I do it through the mask? Hi, since the kelp and water are moving so much on the sand is, when you guys are looking at difference through time, change detection, what are you using for basically georeferencing? Are there spots on land or up in the cliffs that you're using? Because I know that sand is moving in volume and shifting around so much. How do you do that?
Yeah, so there are specific points on the coastline that are pretty static. We try to get quite a bit of coastline in for that reason exactly. That way we can help with georeferencing. Otherwise, if we're only imaging over the water, there is a pretty significant amount of error that's introduced to our orthomosaics in terms of spatial referencing.
Yeah, the same thing applies for the beach. We have structures along the coastline that are captured in the image, so we can use those to for that. But a lot of what we're doing with the beach images are based on the data that we're extracting from time to time. So we don't necessarily need direct overlap in the time from image to image, but having the ability to track that time series using that will help, especially for the high resolution surveys where we're doing daily flights.
Excellent. I think we have time for one more question. Perfect. Thank you very much. It was an awesome talk. And I have actually maybe two small questions. One is the fact that when kelp is growing, does not emerge on the surface. So there might be a significant amount of biomass there. And so how do you account for that? And the second one is about whether you're thinking to integrate your drone imagery with satellite imagery to scale up to larger geographical areas.
Yeah, so of course, that's one major limitation of using aerial data for studying these forests. If it hasn't emerged yet, we can't include or we can't infer anything about what's below the surface. So our calculations are using the relationships between canopy biomass and the amount that might be under the water to estimate what's actually there. But yeah, that's definitely a limitation. Same with satellite data. We're not able to make any estimations about what hasn't emerged yet unless we have information from divers. In terms of integrating the two products together, we've done a lot of work using drone imagery to actually validate our satellite data, but using them in conjunction for scaling would be something that's really interesting to do.
Excellent. Well, I'd love to ask more questions because I know, but we have one more presenter coming in here shortly. I thought this presentation was outstanding, personally. Give him a big hand. Maybe next year we can have you here in person because I know that a ton of the people here would be interested in picking your brains on about more details about what you're doing and the lessons you've learned and the things you can impart because yeah, this is excellent work. Thank you so much.